let's talk about caching. Caching, as I'm sure you already have heard, is about storing data for future use, data that is a bit hard or otherwise slow to compute. So you store that data, as you don't have to compute it again, and by that you gain some performance advantages. Users don't have to wait, your server's load decreases, and thus the throughput increases. So all good stuff. It's not really a silver bullet because, well, first of all, you trade memory usage or some kind of distributed cache usage for time or CPU time or some other kind of resource. And secondly, if you do caching, then you also have to do cache management. You have to invalidate cache entries so people don't see stale data. But all in all, caching can be super useful. It can be a super easy solution for certain performance issues. Don't overdo it and always think about the implications. But for now, let's see how it works in Orchard. What we'll do is that back in our module, we'll create a simple controller to demonstrate caching, and we will use IMemoryCache. IMemoryCache is a built-in service of .NET Core again, but Orchard has the implementation for it. And secondly, Orchard has an infrastructure called Signals, or an API called Signals that you can use to invalidate cache entries. So we'll also take a look at that. All right. So let's create a simple controller for this, just for the demonstration, and let's call it cache controller. And as usual, use the snippet that we have here. And in the snippet, let's inject IMemoryCache. All right, caching those memory. All right, now let's also create an action here. We will actually create two actions to make it clear. First will be to retrieve data from the cache, or mostly read or write the cache, because that's sometimes tightly connected as we have seen, but mostly tightly connected. And secondly, we will have a separate method, a separate action for explicit invalidation. So let's again do a string returning action. So let's call it read cache. Now, IMemoryCache has a pretty simple interface, but it's also pretty powerful. As you can see, IntelliSense suggestions are pretty good already. As you can see, we have basic read and write methods, get set, remove to explicitly remove something from the cache. And try get value follows the usual pattern where it returns a bool, which will indicate whether the entry exists. And secondly, in an out parameter, it will also return the entry if it does exist. Let's do the simple things, and let's do the usual pattern here, and let's use that try get value method with a cache key, and let's retrieve something from the cache. Commonly, we put cache keys into constants. Sometimes even public constants, but then the cache itself is kind of an API that you expose, and usually you want to provide something higher level than that. But at least we put these into, well, at least constants here in a given method, in a given scope, but also commonly into class level constants here. So we can have a const string for a cache key here. Do remember that cache keys are global identifiers. So it's commonly a good idea to prefix it somehow. Nobody will actually read this, And if you are using constant, nobody will have to write it more than once. So it doesn't have to be nice. It just has to be unique. So let's prefix it with the module name, and then let's call it cache controller.demo. So you have some unique key here. And again, try get value has to, well, we need to give the constant a name, of course. And first, here we have to use the cache key. As you can see, the cache key should be an object, or can be an object, any object. Usually, the simplest thing is to use a string for the cache key. So it's more or less also human readable, and it can be easily unique. And then we need the out value here. So, well, let's call it cache entry. And now, if we are inside this if, then the cache entry is already available. Commonly, the pattern is actually the reverse. So if there is no cache entry, then let's create it. Let's create it and let's save it to the cache. So just to make sure that we see that we are actually caching something, let me inject a clock, and we will cache the current date time. Of course, that's not something that you'd usually cache. The point here is that we'll see whether it changes or whether it's the same. We just have to wait 1 second. So let me also inject the clock, but instead of using iClock, I will use iLocalClock just as a change. Local clock is well, it's exactly what the name suggests. It's an injected dependency that represents the current, or that allows you to retrieve the current datetime, but it will be a local datetime, local as for the time zone settings of the current request of the current thread, which by default is the default site time zone. But you can also specify this, as we have seen in earlier sessions, per user or based on some arbitrary logic for every request. So now we have the local clock here. So let's also save something to the cache. And again, we'll use the set method for that. Super simple. First, we'll need to use a key again. So let's use the same cache key. And then we'll need to save the actual data. So let's retrieve the local clock time here. And this is async. So we'll need to make this method async as well as return a task. You know the drill. And we should add an await here too. All right. So if there is nothing in the cache, now we save something to the cache. And commonly the approach here is to also use the value from the cache, of course, or the new value, but use some kind of value. And as you can see, this method returns datetime offset, which is, of course, the same that the local now async returns. So we can have a variable here, which is, again, a quite common pattern. We can have a variable here for that value. So we can have something like the local time, and instead of this cache entry here, we can use this variable, but then we also need to specify the type parameter for its target value, but due to type inference, that's already done. So local time is now read from the cache if it exists, or we can we can supply the variable with the new value if it doesn't. And then we can just return this after I import the namespace for task. So now we can return local time. Well, local time as a string. Not caring about formatting here, just simply to string. So that's pretty much it. But of course, we don't have invalidation yet. And it's possible to invalidate based on time. Well, not in try-get value, but if we take a look at, so let's take a look at cache invalidation too. Now, the simplest way to invalidate cache is, of course, explicit invalidation. So let's call this invalidate cache, and let's do explicit cache invalidation here. And how you do that, we have already seen, is that there is this remove method for memory cache. So again, we can use the cache key here. And we can return a simple OK again, just to see that this has executed. Now, this is of course super simple, and explicit invalidation is of course super useful. So this is all good. I would add one other way of invalidating caches here, and that's via signals, and specifically that because that's an orchard-based thing that's just coming from Orchard, so it's useful to know about. Otherwise, you can read a lot about IMemoryCache and how it works and how can do invalidation, time-based invalidation even. Let's take a look at signals. Now, the issue with this invalidation is that, or this memory cache, explicit memory cache invalidation, is that you have to know that the entry is in memory cache, because you have to use memory cache, access memory cache, and run memory cache.remove. Now, you could have some kind of abstraction above that and have your own local datetime caching service or something like that. So when you want to explicitly invalidate the cache entry, you'd call a method on that service. So there is no direct dependency on IMemoryCache, because the caching implementation can change. Well, first of all, the implementation of IMemoryCache can change, but you can also opt to switch to a distributed cache. So you'd use some other service here. Now, to overcome all of this, there's one simple, very generic way of propagating signals in the system, in Orchard. Not just for cache invalidation, but that's a prime example of actually using them. Signals are exactly what the name suggests. You raise a signal, which means that you pretty much say that the signal with this identifier, like a string, is now raised. And everybody listening to that signal will get the memo. It's a tiny bit like an even pass. You could also think about it a bit, but it's called signals. So let's see how that works. Let me create another method here for signal-based invalidation, and then we'll test the whole thing at once. So let's call it with signal. And what we'll need to do is that we'll need to inject ISignal here. ISignal, we won't need memory cache here. So let's inject ISignal into the constructor. Yeah, unfortunately, that's this constant here throws off the dependency injector a bit, but anyway, we have it here. So let's see what ISignal has. And well, it has a couple of methods and a lot of extension methods that are actually unrelated. What's important here is the get token and signal token. These are basically the read-write or the listener, and then how do you call the other part, methods. So basically, when you want to braze a signal, you would call this signal token, and when you want to tie, for example, the invalidation of a cache entry to a signal, you would use this get token. So let's do the first part, tying the cache entry to the token. So we have this memory cache set here. It's an explicit set. It can only be explicitly invalidated. But we can also do time-based expiration here, as you can see. There is also a lot of options available that you can read about, because this is just .NET Core thing, not really tortured. And there is also this change token-based invalidation. So that's what we'll use. We can pass signal.get token here, which you see retrieves an iChange token here. And we also need a string key here. So again, this will be a global identifier, so we can use something like this again. But this won't be a cache key. This will be a signal key instead. And let's call it demo signal. And we can call the other one actually demo cache entry to make a bit of a distinction. So in get token, we need to supply this key, which is now done. So create, we now tie this cache entry to this signal, or this signal's token to be specific. That doesn't mean that this explicit removal won't work. It still will. So we just gain another option to invalidate this cache entry. And we will actually do that here. So we can call signal token here with the same key, of course, to raise this signal, and then the cache entry will be invalidated. Do note that there is nothing about caching here. This is just raising a signal. You can actually raise a signal from a workflow as well. So this is a quite simple way to tie your module into workflows, or expose a very generic API for your module that is usable from any module without taking a dependency on your module, because you just need to use signals, or even from user-facing features like workflows. So very, very useful. And of course, signals are these change tokens. Change tokens are quite commonly used with caching, but that's not the only thing you can do here. You can again use them as kind of an event bus. But for now, let's start the application with Control F5, and let's see how all of this works in the end. Back in the browser. Now we will need to open this controller here. So again, same pattern Dojo Course.module, and then read cache and the two invalidate caches. So let's first check out read cache. And it's not found because it's the cache controller. It's called cache controller, yes. So we of course need to add cache there as well. Okay, so this is indeed the local timestamp here. You see +2. I'm in UTC +2 hours, Central European summertime. And if I hit refresh here, it doesn't change. So caching actually works. Not a huge surprise, but, well, you know, little successes. And now let's open the invalidation methods. So let's first open this explicit invalidate cache and let's see whether that works. So, invalidate cache, okay, something happened. Now let's refresh here, and you see it worked because it's now a different time. Let me put this to the side so we can do it a bit faster. All right, and watch it here. It changed. Pretty cool. And now let's do the signal one. And let's refresh here, and again, it changed. Let's try again. It changed. So, great, caching works. One note here, of course, this is just a simple demonstration. First of all, you can check out the training demo again for more details, for more examples. There are also more caching options in Orchard, as well as in .NET Core. There's distributed cache. There is something called dynamic cache in Orchard that you can use to cache shapes, for example. That's also used for do not caching. And also do note that since this is just a simple demo controller, these methods are just get methods. In real life, if you are doing some server state altering operation like invalidating cache entries, and you happen to do that, somehow connected to a control action, of course, this control action shouldn't be get, but something like post or maybe delete. Use the HTTP delete method. All right? But these are the basics of caching, and now you have a very powerful tool, but remember, it's not a silver bullet, don't overdo it, but still you have a very powerful tool to increase the performance of your applications. If you are doing some heavy lifting, there's some very involved computations, you are fetching a lot of data and then doing something with it, or you are fetching data from a slow data source like a remote API that takes a couple hundred milliseconds or couple seconds even, then do cache the result of these operations. Caching can be very useful to increase the perceived performance of your application. So your application will appear faster to users. When they click something, it will happen faster. Secondly, it can also greatly increase the throughput of your server because you reuse on computations, you just compute the heavy lifting once every 5 minutes or something like that. Then you are doing the caching, so your server have a smaller CPU load, or sometimes even memory loads, and that means that your server can serve more people with the same amount of hardware resources. And that's a very useful thing.